So first of all, what's a tidal disturbance? Like Daniel and Beck have mentioned about this, but they didn't introduce them in detail, so I'll do it now. So it happens when we got stars that like very close to a supermassive black hole in the galactic center and got disrupted. So then it formed a debris stream, and due to the strong general relativistic effect, the stream will be like processed, and it will hit onto itself and form some collisions, and then cause a rapid dissipation and circularize around the black hole to form sort of a accretion disk, which will be accrete onto the black hole and release some X-rays. So what's the problem with TDs? We expect to see X-rays from the accretion, and we do see that, but more than that, we see them in optical, in infrared, and in radio. And also, there's some observation about the PV neutrinos that also coincide with previous observed TDEs. So we still don't know if that's from the same source or like just a coincidence. And with the neutrino, like the process of forming neutrinos, I expect to release gamma rays, which are not observed yet, but possibly. But the real problem is all the TDs are really far away from us. So even the galaxy itself is like close to a point source, not even to say the TD itself. So how can we observe TD and study them? So that's through observations. Sorry, through simulations. So here are some observed light curve and inferred black body radius and temperature from the optical observations of TDEs. So if we try to infer something from these observations, we can, like the TDE is kind of like a supergiant star with a diameter of around 100 EUs. So it's like different to the initial expectation from TDEs. And we're still not too sure what's actually happening there, but kind of get some ideas. So onto my simulations. So we run simulation with GSPH, and we launch a MESA one solar mass, one solar radius solar star to a 10 million solar mass supermassive black holes. And just to save times, we choose an orbit with eccentricity of 0.95, which like in general case, TD it is expected to like dominated by parabolic orbits, but this is just in case of times. And we also launch like really close to the black hole, which is like characterized by what we call penetration factor beta, which like 5 is like really deep to the black hole, so really strong disruption. And all of these parameters are just to save times for the simulation because the times down here are fast. So to see the simulation, we have a star here, and we have a black hole in the middle, which you can see this is black. And then we launched that to the black hole, and it got disrupted into a debris stream, which then fall back towards the black hole, and due to the GR precession, it like hit itself and form a collision, like strong shocks, and then suddenly boom, it forms some accretion disk. So that's a close-up, but if we look like zoom out and look really far away, so here I've got a box, which is the view in the last slides, and this is still the same simulations. We see there's a lot of outflow going on, and outflow is like quite fast with 0.1 speed of light and hot at like 10,000 kelvins. So if we try to add some opacity to see what we actually see in reality, we see like we do get something kind of like a supergiant star, which is similar to what we expect from the observations. So because we don't resolve those things in reality. So the only way to compare simulation with the observation is trying to do some post-processing, do the ray tracing to form like synthetic spectra and light curve to compare with the observation. So we do them with post-processing first flash, and we do the radiate transfer, and we choose the source function to be black body emission and the opacity to be the electron scattering opacity. And then we got some spectrum, which I've got a pink shaded region here representing the actual observation, like observing range from the real surface. And so instead of the whole spectrum, we actually see from observation is only this part. And we see as it evolves and like fluctuates a lot. And here I've got orange dotted line, which is like we try to fit a black body to this pink region. That's what they are doing in the observations because we only see that part and they assume that's a black body and something to it. So you can see like this off by pretty much in the UV range. And then we do the light curves. So here the lines are our synthetic light curves, and we got those dots, which are the real observations. So we see in general the luminosity does agree with the observed range, but the black body radius and temperature is like off a little bit. So one problem here is like with the opacity, it's like we're a little bit unsure because we expect the region to be really dense in electrons, so there will be like a separation between the last scattering radius and the last scattering radius and the other, I can't remember the name. Sorry, I can't remember the name. But like the separation of two layers that cause the temperature and radius to be off by a little bit. Yeah, so that's the optical part. So we also try to use the same simulation to produce the radio observations to prove like all those observations are actually from the same source. So how we do this is like we took the Arduino simulation and we took those outflows, and in a separate simulation we have set up this like circumnuclear material or like just some interstellar material like within the galactic center. And we launched alpha from the pre-simulation from the middle out and try to observe the interaction between the alpha and the CNM shell. So here is a temperature random video with some opacity to see like what we will see like, in the radio range if we can actually resolve the thing. And we see like, so that's the front of the interaction. So we do actually form like a hot shell that's like due to interaction between alpha and the radio emission are like expected to form from this hot region. And here we haven't done any post-processing yet. We're just looking at the simulations because in the observations they also like try to infer some like alpha properties from the observations, but we do have the simulation so we can compare that directly. And here like the lines are from our simulations and these dots and shaded region are from the observations. So the shaded region represent their like those different assumptions used in inferring the alpha property from the observations, because we really have no idea about how the alpha looks like. So they got like quite different assumptions. And we can see like in general, the radius does agree, the velocity does agree, but the energy, like they got a bigger energy range, which could be possibly related to the initial star, because we are always using the same initial star. And some inferred black hole, sorry, magnetic field, which is also like a small range compared to the observations. Yeah, so we do the same ray tracing again, but instead we are using slowly synchrotron spectrum as the source function and like radio self-absorption as the opacity. So then we produce some synthetic images. So as we see in the last temperature video, like the hot region is all over there, but the actual emitting region is like just a small part from them. So it also relates to the density of the thing, like besides temperature. So we also get some spectra, which like here still the lines are synthetic spectra, and the dots and dotted lines are from the real observations. So they kind of agree to the similar order of magnitude, but the detailed evolution is still off by quite a bit. So what we think is going on here is like in our simulation, we are still doing adiabatic. So we haven't included any cooling yet, which we expect to be important in those regions where the density is low and the temperature is high. So yeah, we need much more simulations to say something. And here is like how the peak frequency evolve through time, which again, like the lines are synthetic ones and the dots are from observations. So as you can see, like all our synthetic evolution got the same trend. Doesn't matter what's the parameters we use, but the real observation got like a lot more different trends. So again, we're not sure what's the cause here, but potentially like the black hole or the star, like which doesn't vary at all. Yeah, so I've also got some preliminary results for the new thing. So we expect like people expect the radiation pressure to dominate in this region for a long time because it's low dense and hot. But from up till now, we are only doing simulation with like gas pressure and as adiabatic. So we try to include radiation pressure into that. So if we don't have GR, it's pretty simple. We just got one more term here, but then we do have a lot more complications with GR, which I'm not going to detail here. So here are some videos that's comparing with simulation without radiation pressure and one with radiation pressure. So this one is for the same simulation as we showed in the last two projects. And as you see, it's pretty similar at the beginning, but in the later part, like the radiation pressure does smooth out the alpha a lot. So it doesn't have as many structure as the one without radiation pressure. And so here's another one that's for like a parabolic TE, which we also see the similar thing. Like it's pretty similar at the start. And then in later time, we see we got a lot of density structure in the one with radiation pressure, but with radiation pressure, it's much more smooth. And we also try to, sorry, I don't know what's that. We also try to run some light curves, which on the left are the things without radiation pressure, and on the right are the ones with radiation pressure. So as we can see, like it doesn't change the lumen, it doesn't change the temperature and increase the luminosity and blackbody radius by a little bit, but not much. So the main difference is like we got a lot of fluctuations here with our radiation pressure, but it's like much more smooth with radiation pressure. So similar to what we see from the density structures. And yeah, that's the main effect we see from the radiation pressure. For now, we are going to do some more analysis, which is haven't done them yet. Yeah, so the summary is like we use the same simulation to form a unified picture of the optical and radio emission from TDEs. And we also look at the effect of radiation pressure, which it does smooth the density structure and like this.
Thanks for the nice talk. I just want to ask about what's exactly happening. So, when it tidally disrupts, the reason it shines, you're saying, is when it goes back and does another orbit around the black hole, it collides with itself, with remnants of itself. Is that correct?
So it does collide, and there's like debating about what's the first light from TDEs. So some people say it's like the optical emission is from the self-collision itself, but from what we see from in the simulation is like you got accretion first, and then you got X-rays, and X-rays absorbed by the surrounding gas, and the surrounding gas then release optical. So it's basically like from the accretion itself.
From the accretion. And would that be less if it's not in GR? Or do you need the precision to cause this?
Yeah, like the role of the precision is like to accelerate the circularization. So if you don't have GR effect, it remains in its orbit for a long time, and then like dissipation smooths out the thing, and it will finally start accreting, but the time scale will be much longer.
So for when you did the comparison of the light curves to the observational data, there was like some mismatch. Like, can you talk about like the processes that might be missing from the calculations that have been achieved?
So we do have a lot of things missing from the simulation itself. First, like as I said here, we don't have radiation pressure at all, and also we don't have like cooling the later time, which both like affect the things. And also like when we do the simulation, when we do the post-processing, we are a bit like unclear about what's the opacity we should actually use. So people expect like electron scattering to be a dominant source, but still like how dominant is like a little bit unsure. And I do have a slide here. So yeah, so in the case of TDE, we got this like separation of photosphere, which like you got things like emit, absorb until like the last absorption photosphere. Now it's not absorbed anymore. It got like scattered around until released to be seen. So the detail about those like separations are really not clear.
Little follow-up question. So, I mean, you have a gazillion particles with the APR Fangyi, right? So, but have you checked the effect of resolution at the layers of interest where you're making your radiation, where the radiation escape from?
Not yet, because like for the APR, what we have from is only the initial like the first paracenter passage. And for the radiation to start, we need to wait till the accretion, which when we are around those APRs, like the merging there is not that accurate yet. So we didn't run that further. Yeah, that would be something we need to check.
Yeah, definitely. Because if it's, I mean, this is completely different situation to us, but it is the resolution and where steep temperature gradient is, like at the photosphere, that is the problem.
Yeah.
Question? If not, let's thank Fitz again.